everybody good on this now? Okay. Just about done. Let me just go through the two other items that are on this problem, and then I think I'll probably call it a night, because it's getting late. And I still got to finish grading those tests too, so if I don't get that graded, I'll be. You won't be very happy with me. I'll have them back by tomorrow, assuming I get out of here. This one, this is part C. Let's suppose that A is a 4x4 matrix and B is a 4x4 matrix. And let's suppose that the determinant of A is -2 and the determinant of B is 3. Here's a question. Find the determinant of A inverse B transpose times the matrix 2B inverse. So this is just reviewing properties of determinants, and this is not a particularly hard problem, but it's been a few weeks. So I just thought it would be worth double checking. In fact, I may even have done this exact problem before. It looks kind of familiar to me, but that's okay. Really quickly, how does the transpose affect the determinant of something? It does nothing to it, right? Leaves it the way it was. What about inverse?
No.
Say again? No. I thought I heard somebody else say it. Yeah, flips it. The reciprocal. You take the reciprocal, right? So it flips it over. So in other words, if I can find the determinant of 2b, then I just flip that over, right? To get 2b inverse. What about under multiplication? I have two matrices multiplied together and I want to take the determinant of the product. What can I do?
Multiply the determinants.
Do the individual determinants, right, and then just multiply the results. Exactly. So that's really what you want to do is just break this down. Okay? So let's see if we can, I think I've talked about most of the properties here. So for A inverse B, what will be the determinant of A inverse B? So you're going to take the B, which is 3, and you're going to flip the -2 over. So you're going to get -3/2, right? Does the transpose do anything to that? No. Times, now I have to flip over, put it on the bottom here, the determinant of 2b. What's the determinant of 2b?
-6.
6? Oh, 6. Got to be careful. Caught a few people here. Remember that this multiple of 2, every time you multiply a row, a single row of a matrix by a constant, the whole determinant goes up by that constant. So if I have 4 rows and I take 2 times the matrix, I've really multiplied by 2 4 times, right? So I have to take this 3, determinant of b, and multiply by 2, by 2, by 2, and by 2. Right? So that's actually going to come out to 48. I'm pretty sure we did this example before, but that's okay. So this is, whatever, negative 1 over 32 or something. You simplify it. Yeah. Okay. So that's a good one. All right, and I got one more here. Again, maybe you realize you're a little rusty on this. If that's the case, that's okay. We got 6 days to hammer it home and go back. And the purpose of the review is not to make you perfect tonight, but to remind you what you need to review so that then you guys can study it and focus on the things that you're having problems with. Okay, so I got one more here. So this is part B of the same problem. I have x prime equals, this is a linear system now, 2, -1, and 2, 4 times x. And my question here is, as t goes to infinity, so if you let time go forward, do x1 of t and x2 of t approach the the origin, which is 0, 0. The x1, the x1 of t and x2 of t should not have vectors on them because those are scalar functions that make up the vector x. So take off the arrows on those. Does anybody
Yes.
know how to do this problem?
Yes, sir. It is.
Hold on. I'm not ready. Too fast.
On the eigenvalues.
Find the eigenvalues, right? So I find the eigenvalues, 2 minus lambda, -1, 2, and 4 minus lambda. We've been doing this a lot lately. Okay, so I take the determinant of that. So I'm going to get 2 minus lambda times 4 minus lambda, and then plus 2. Agree?
Mm-hmm.
And so this becomes lambda squared minus 2 lambda and minus 4 lambda is minus 6 lambda. And then we have plus 8 plus 2 is plus 10. Okay? So if I want to find the eigenvalues of this quadratic, how am I going to get them?
Quadratic.
This one does not factor nicely. Does not factor nicely, so I'm going to use a quadratic formula. So I change the signs of 6 plus or minus the square root of 6 squared is 36, minus 4ac, that means minus 40, all over 2. Agree? So 6 over 2 is 3, and radical of -4 is really 2i, and I'm dividing that by 2, so I'm going to get I. So these are my lambdas. These are my lambdas. Complex numbers. Oh boy. So do we know, does anybody know yet what is going to happen? Do we need to find the eigenvectors?
No.
Say again?
2 positive exponents.
We've got positive exponents here. Let me show you why. Remember that the way you get your solutions, here is you do the e to the lambda t times v. V is just an eigenvector, and that's like a constant vector. That doesn't change with time. That's just a constant vector. The lambda is just this lambda right here. So 3 plus or minus I times t, and then times v. The key point here, guys, is if I sort of expand this exponential piece, I'm going to get e to the 3t, and then I have e to the it. But see, e to the it is just cosine of t plus I times the sine of t. And then we have v here. I'm not even going to worry about v yet. I didn't find v, so I can't do anything with it, right? But would you agree that this part right here is just spinning in a circle? It's not going towards the origin or away from it. It's just kind of going around every 2 pi units, just going around the complex plane. And the v is also not moving, right? That's just a constant vector. So I have a constant vector times some scalar multiple that's just sort of, it's almost like you have a vector v here, and it's being scalar multiplied by something that's kind of going back to where it started every 2 pi units. So you keep coming back to this vector. And the vector basically gets spun around or something, right, as this thing goes around a circle. But what is really the driving force that allows you to answer this question?
E to 3t.
This part, right? And this part is, that 3, that is the crucial thing, right? The 3, that's a positive 3. So that when t goes to infinity, what happens to this exponential term?
Just in origin.
It blows up, right? It blows up to infinity. So actually the correct answer for what happens to this system is basically it spirals outward. Goes around in a circle, but it gets blown further and further away from the origin. It keeps coming back to the same orientation every 2 pi units. But every time that it does that, its scalar in front, the e to the 3t part, has become that much larger, which means the vector is stretched that much longer. So it keeps coming back around, right, but with longer and longer reach. The answer here is no, they do not approach the origin. If I wanted to have the solutions approaching the origin, I would need a negative in front of this real part instead of a positive. Does that make sense? Usually these questions about, well, what happens as t goes to infinity, or questions about the phase portrait, those kinds of questions can usually just be answered from the lambdas. You don't have to go into solving for the eigenvectors to be able to address that. You just need to find the lambdas. Are they positive? Are they negative? Do I have one positive and one negative? Right? That's where you get the sources and the sinks and the saddles that we've talked about. But even something like this, where you have lambdas that are complex, it really comes down to the real part of that complex number. If it's positive, the solutions are going to go away from the origin. And if it's negative, then they're going to spiral towards the origin. So you have sinks, sources, and saddles, but you also have spirals that go outward or inward, or if there is a zero on that real part, then you just stay on the circle, right? Then basically this part isn't there, and you're just circling around. Every 2 pi units, you're back where you were before. That make sense? Okay. So I just thought I would give you a quick example on that. Highlight that again. I think I've done pretty well with getting through the sheets. There are a few, I mean, I've probably done about 2/3 of the sheet. To tell you the truth, I've not done everything. I've done 8, 9, 10, 11, and 12. I did all the last 5. And I did number 1, 4, and 5. So there's a couple others there that I didn't do, but that's all right. What you guys can do is practice them on your own. And remember that you can reach me remotely through email. You can call me. I'm going to give you my contact information and when I'm going to be available. Some of you have me on Facebook.
Yeah.
Send me a Facebook question. That's quick. Pretty much logged on.
You're always on Facebook.
Yeah. But I think that's about all the energy I've got for tonight. So.